Welcome back, everyone. Next up, we have Vander from PixElement. He's going to be briefing on overcoming calibration and geometric alignment errors when integrating photogrammetry with LiDAR and UAS data acquisition. So please welcome Ben.
Thank you. All right. Good to see everyone after lunch. So as you can tell, I shortened the title a little bit, simplified it to be making the most of LiDAR and photogrammetry with SUAS, so small unmanned aerial systems. Just a little bit about me. I'm Ben Vander, founder of PixElement, which is a photogrammetry and geospatial software company that offers both cloud-based and standalone software modules. All right, so today it's about integrating LiDAR with photogrammetry. All right, and hopefully by now, I don't need to pontificate about the differences between photogrammetry and LiDAR after 3 days of rigorous discussion. And in the interest of time. But the biggest thing I want to call out in this slide is that with LiDAR, we're typically talking about direct georeferencing, okay? Direct georeferencing and consistent data regardless of weather, lighting, vegetation. Whereas with photogrammetry, we're talking about indirect georeferencing. Passive sensor needs an illumination source and very, very low cost, images, but yes, indirect georeferencing versus direct georeferencing for LiDAR. That's going to become kind of a theme in this presentation. All right, so from a raw deliverable standpoint, we've got, if you look at a typical deliverable from LiDAR, you're looking at a 3D point cloud, and maybe a derivative from that would be a DEM or a DSM, DTM, but those are your kind of raw deliverables if it's just LiDAR by itself. Planimetrics, topographic information can be derived from that. With photogrammetry, you can generate, via dense image matching, you can generate colored 3D point clouds, 3D textured meshes, orthomosaics, etc. All right, so you've got more outputs and more products available from the photogrammetric workflow than you might have from LiDAR by itself. All right, so just to kind of give you a broad overview, we primarily focus on, we're commercial facing, okay? So we work with surveyors, construction companies, civil engineers, and we're seeing a lot of LiDAR adoption out there in the industry. There's a considerable amount of hype around, putting a LiDAR on a UAV and flying it around and getting high quality, high accuracy data. However, a lot of these customers do not have a deep understanding of LiDAR or photogrammetry at all, and what the strengths and weaknesses are of the different technologies and really what to expect. So they run out, buy a $40,000 system, come back in and start looking at the data, and they're like, well, this isn't making sense. Can you help us make sense of it? Okay. So what we've seen is if you do it correctly, we've seen the differences between photogrammetry and LiDAR, but our goal is to fuse them, to unify them, to bring them together, and to get the best of both worlds with these combined drone LiDAR and photogrammetry payloads that are becoming a lot more prevalent in industry. And the reason we want to do that, well, multiple reasons, but downstream extraction, right? So machine learning based feature extraction, very, very dependent on having consistent and accurate fusion. All right, so what are some of the challenges we encounter when integrating photogrammetry with LiDAR? We have datum errors, geometric errors, radiometric errors, and really temporal differences as well. But we're just going to focus on those first three today. And the biggest problem is that there's a lack of awareness amongst the user base about how to correct for these errors. All right, so from a software perspective, we don't build hardware systems. We're purely software. So to some degree, we're at the mercy of hardware vendors. We have to be agnostic we don't just work with one system, we have to work with dozens of systems, all with their own characteristics. And so by definition, this excludes us from doing direct georeferencing, okay? So a lot of vendors gatekeep their raw data, so we don't have access necessarily to the LiDAR ranging or the navigation data stream. So we can't get our hands dirty on the direct georeferencing front. And as an aside, you know, if I was to go to therapy today, you know, I would probably be talking about proprietary data formats, because it's something that comes up with us all the time, right? We have to design solutions over forms of data that we have access to when we prefer to, you know, deal with the raw data directly. But our approach is to correct for these bore site calibration, bore site alignment errors, camera calibration errors, using an indirect georeferencing approach that leverages bundle block adjustment and the strength of photogrammetric blocks, okay? The one caveat is that this assumes images have sufficient overlap for, you know, 3D reconstruction. First issue that we'll show, datum errors. So everyone thinks, well, I bought a $40,000 system. You know, my photogrammetry is going to come in aligned with the LiDAR. Now, it very rarely happens, okay? So a lot of times we'll see a situation like this where you have three different height sources of information or height data. You've got the LiDAR that might be on ellipsoidal height. You've got ground control points that are on maybe orthometric heights. And then heights in the image metadata that we don't know where they're coming from, somewhere in between. And so we have to, in the software, account for this automatically, right? Solve for these datum offsets and fuse these together to build these downstream deliverables. So the first step of doing that is measuring tie points or ground control points, most commonly between the LiDAR data and the images, okay? So that's the first step, is you have to, you know, have observations from both the images and the LiDAR. And then we solve for these data misalignments as additional parameters in the bundle block adjustment, okay? And most commonly, we're solving for, usually it's either one 3D bias or a set of 3D biases in the data. But sometimes we'll get, for example, ground control points that are in the local coordinate system. And so we can also add Helmer parameters to, additionally to the bundle adjustment to solve that translation and rotation into a different system. So what that typically looks like, if you know, for the photogrammetrists or the math folks in here, is when we set up our system of normal equations, we've got our, you know, extrinsic, our camera parameters, then we've got our ground points, and then our intrinsic parameters, the camera calibration parameters. And so we add these datum offsets as additional parameters to that block adjustment. All right, so that's how we account for datum misalignment errors. So once we snap those data sets together, the next thing we have to address is geometric errors, okay? So, well, what does this look like in the wild, right? So a lot of times these cameras are included with these LiDAR payloads, but to colorize them correctly, like I said, you need to know the camera must be calibrated, the bore set alignment must be known, and you have to have very good direct georeferencing, which we don't have access to. So we can't correct it at that level, but we can correct it at the, you know, by leveraging, you know, bundle block adjustment. And so in the wild, this is what you see with geometric colorization and geometric errors in colorization. So these are real user data sets that you can see where they've collected the LiDAR data, colorized it with the direct georeferencing information, and you've got massive shifts. Well, you've got some shifts that might be on the order of, you know, decimeters going up to, you know, 5 to 10 meters. And one thing that we can say definitively is that every hardware vendor we've tested so far in the UAS community has this problem to different degrees of errors, but it's prevalent in every data set we've looked at. Okay, so I don't think NGA would be necessarily happy with with data that looks like this coming from these systems. All right, so to correct for this, again, this is the direct georeferencing approach. You essentially at time t, you're projecting that camera down into the point cloud, and any errors that might be present in that trajectory solution at that time impact how that LiDAR data is colorized. Whereas with indirect georeferencing, we don't have that problem, okay? And so what ends up happening is using the bundle block adjustment, we can get very tight orientation, a solution for the orientation parameters, and recolorize the LiDAR point cloud using that photogrammetric block. Okay, again, a very similar workflow where you have to measure tie points and ground control points, but then by integrating that together, you can do this. So here's the before. So that's the uncorrected point cloud from the hardware, they're the LiDAR vendor. On the right-hand side, we have our recolorized corrected point cloud. Before on the left, after on the right, and then once more, okay? So that's correcting for geometric errors in that colorization. And it's very important because, like I said, a lot of downstream workflows work on matching up either based on colors, based on intensity, usually a combination of both. And so when you have these big shifts in linear features, it's not correct. It's not, it causes a lot of issues, okay? So the next issue I wanted to look at was radiometric errors. And you might think, oh, well, why do we want to do that? It's not really all that important, but people care about the aesthetic look of the data you're generating. Okay, so again, this is real data that we get. So you can see how the vendor colorizes the data. So they're just, at that point in time, they project that image down and just color that small area. And they do it with a single image at a certain point in time. So our goal is to have a more intelligent workflow of correcting for this radiometric error using the bundle block. So again, we utilize the aerial block. So once we've determined the position and orientation parameters of those cameras while that LiDAR payload is flying, we can overcome these illumination errors. And the reason we can do that is because we can actually take that LiDAR data and do view assignment and determine exactly which LiDAR point is viewed by which cameras, okay? So once we do that, we normalize the color of all cameras that are viewing that LiDAR, that specific point, and generate a much more unified radiometric colorization. So here's what that before looks like and after, and again, before and after. So again, we're just leveraging the strength of the bundle block adjustment. All right, so we talked about some of these errors that commonly come up or always come up in the data, but some of the unique downstream data products that you can generate, the value add data products you can generate by combining LiDAR with photogrammetry are 3D textured meshes. Okay, so from this LiDAR point cloud, we can generate highly detailed, highly realistic textured meshes by integrating that camera information with the LiDAR data. And because we've solved for that, those data misalignments and established the correct view assignment for each point in that point cloud, we can generate very, very accurate 3D meshes from this data. We can also generate orthomosaics. So up top, we have the point cloud over this densely wooded area, but we can also, because we have imagery to go along with it, and we've unified these two data sets, we can generate orthomosaics, blended orthomosaics that are accurate and also aesthetically pleasing. All right, so the benefits of indirect georeferencing are that it allows for registration of LiDAR and photos to ground control, even if they're in disparate systems. It's a very flexible method, so that's the reason we love it so much, is that we can add different sets of parameters depending on the needs of the users. And when I talk about flexibility, I primarily showed drone LiDAR scans with photogrammetry, but we can also merge ground LiDAR scans with, for example, phone imagery, with aerial drone imagery. We can do drone LiDAR scans with drone images and airborne scans with airborne imagery. Okay, and again, why do we do that? A lot of these users spend tens of thousands of dollars on these systems and then actually start looking and interrogating the data and are very, very unhappy with it. Now, look, it's not limited to, I know the title of this talk was unmanned aerial systems, but it's not limited to UAS. We can apply the same concept to airborne imagery. So this is a data set from downtown Miami. So we have LiDAR data, and then we only have nadir imagery. Okay, so, and the LiDAR data, if you interrogate it closely, you'll see that it's different spacing, nadir imagery, and yet we can generate a very detailed 3D mesh from that, directly from that LiDAR and nadir imagery. So typically you'd be generating this from oblique, but we're doing it directly from nadir imagery. So some of the future areas to explore, can we apply this method to other data, LiDAR and imagery sources, maybe at the satellite level? Of particular interest to us is, can we exploit the aerial block to actually get closer to the hardware side of things, to correct for LiDAR misalignments, to actually do strip adjustment with by utilizing this bundle block. And there's a few other areas that we're looking at that we see a lot of promise from a fusion and integration standpoint that we're hoping to address. If you'd like to test it out, feel free to just go to our website. Like I mentioned, it's available in the browser. It's available on desktop, and we love working with new data sets and new applications that we haven't thought about. So thank you very much for your time. Any questions?
Hey, I'm curious about the tying process. How automated is it to get ties between the imagery and the LiDAR? What kind of density do you need?
So one thing we're looking at is actually automatically register, because one thing that's come up with our user base already is that sometimes they'll neglect to measure the LiDAR. They'll measure the photo points and they'll forget to measure it in the LiDAR data. And so we thought, well, can we do that directly, right? Just eliminate that need. Once they measure in the photo, find it in the LiDAR. And in general, we can do that if they have clearly defined targets. It becomes a problem when, again, we're dealing with users that might not know the principles of LiDAR. So they might be setting targets that don't have any reflective properties, and then it makes it difficult to automatically register that, or to measure it automatically without them identifying it. Resolution, you brought up another good point. So resolution, right? That is a problem, right? Because the point spacing of LiDAR data may be different than, for example, the GSD of the imagery, right? So when we're building, for example, depth maps from the LiDAR data and fusing it, you've got LiDAR data maybe with a specific density or resolution versus the imagery, and it kind of creates some problems. In general, with the drone data sets, they come in at relatively the same scale, but working with airborne data sets, we're seeing a lot of variability there, and it's kind of something we're addressing right now.
Thank you.